Example: find and classify all the critical points. For fxy is equal to 3x squared y plus y third minus 3x squared minus 3y squared plus 2. Firstly, we derivative f for x. Fx is equal to 6xy minus 6x, and then fy is equal to 3x squared plus 3y squared and minus 6y. If you want the critical points, we equal to these equations to 0 and solved these equations together. Firstly, first equations, six x y minus 1 is equal to 0. So x is equal to 0 or y is equal to 1. We can plug this into the second equations and solve for the remaining variable. For x is equal to 0, second equation is 3y squared minus 6y is equal to 0, and then 3y y minus 2 is equal to 0. So y is 0 and y is 2. For now, for y is equal to 1. Three x squared minus 3 is 0. X squared minus 1 is equal to 0. So x is equal to minus 1 and x is equal to 1. We have the following critical points. Critical points C1 is 0, 0. And C2 is 0, 2. Because firstly we find x is equal to 0, x is equal to 0, and y is equal to 0, y is 2. And then for y is equal to 1, we find x is equal to minus 1 and x is 1. So that critical point 3 is minus 1, 1. And critical point 4 is 1, 1. They are the indicators for local extrema. Next, we use the second derivative test to determine the nature of each of these critical points. We begin by computing second order partial derivatives. F x x is equal to fx is this, and fxx 6y minus 6. Fyy is equal to 6y minus 6. Fxy is equal to, according to Schwarz theorem, fyx and is equal to 6x. So d1 is equal to fxx. So is equal to 6y minus 6. d2 is determinant. We calculate easily this determinant. F x x f x y f y x f y y. So f x x f y y 6y minus 6 square and minus 36x square. d1 and d2. To test point C1, 0, 0, we compute C1, 0, 0. D1, 0, 0 is equal to minus 6. Is smaller than 0. D2, 0, 0 is equal to 36, is bigger than 0, from which we deduce that C1 gives rise to a local maximum. Local maximum. Because D2 at point 0, 0 positive is bigger than 0 and d1 is minus 6 is smaller than 0. This is local maximum. Next, to test the critical point C2, 0, 2. We compute d1, 0, 2 is equal to 6, is bigger than 0, and d2 0 2 is equal to 36 is bigger than 0. Bigger, bigger. We say that C2 yields a local minimum of F. Local minimum. Because bigger and bigger. Similarly, for C3, critical point 3, minus 1 and 1. We compute D1 is minus 1, 1 is equal to 0. And D2 is minus 1, 1 is equal to minus 36. Minus 36 is smaller than 0. Implies that C3 is a saddle point. Saddle point. Finally, for C4, 1, 1. We compute D1, 1, 1 is equal to 0. And D2, 1, 1 is equal to minus 36. Is smaller than 0. So, C4 is also a saddle point. Saddle point, local minimum, local maximum. Now, another example. Find the absolute minimum and absolute maximum of f xy is equal to xy minus x minus y plus 3 on the triangular region with vertices 0, 0 point, 2, 0 point, and 0, 4 point. Zero, 0 point, 2, 0 point, and 0, 4 point. Region, this area. A, B point, X, Y. First, we look for critical points. Fx is equal to y minus 1. Fy is equal to x minus 1. If you want to calculate the critical points, we equal to 0. We equal to 0. And y is 1. X is 1. C1 is 1 point. This is candidate for absolute extrema. We don't know now. Maybe absolute maximum, maybe absolute minimum, or just only local extrema. Now, the boundary of region consists of 3 straight line segments. 3 line segments. This is boundary. First boundary is the boundary on the x-axis is defined by y is 0 and x 0 is equal smaller than x is equal smaller than 2. On this boundary, the values of f can be expressed as a function of x alone. Say gx is equal to 3 minus x, because y is equal to 0 and y is equal to 0, 0, 0, 3 minus x. The critical points of g functions are given by derivative of g is equal to 0. So, derivative of g is equal to minus 1 is not equal to 0. There is no critical point in the interval. We should evaluate g function both at critical points and at the endpoints. Endpoints is these points and these points. 0, 0 point and 2, 0 point. The boundary on the y-axis, now boundary on the y-axis. The boundary on the y-axis is defined by x is equal to 0 and y is bigger than 0 and smaller than 4. On this boundary, we use the function hy. Hy in place of fxy. Hy is equal to 3 minus y, because now we write x is equal to 0. X is equal to 0, 0, and 3 minus y. 3 minus y. And y is bigger than 0, smaller than 4. This function has not a critical point, because derivative of hy is minus 1, is not equal to 0. But the endpoints 0, 0 and 0, 4 are the candidates for absolute extrema. And finally, the third segment of the boundary, this line. This is y is 2, 4, 4 minus 2x. The boundary y is equal to 4 minus 2x, and x is bigger than 0 and smaller than equal 2. On this segment, we will define a new function as follows. M function, mx. Now, we write this function for y. Y is equal to 4 minus 2x. Mx function is equal to f x 4 minus 2x instead of y is equal to minus 2x squared plus 5x minus 1. Critical points given by derivative of m function is equal to 0. So, derivative minus 4x plus 5 is equal to 0. X is equal to 5 divided 4. So, this is y. So, y is equal to 4 minus 2 product 5 divided 4. So, is equal to 3 divided 2. And point is 5 divided 4 and 3 divided 2. A candidate for absolute extrema. Also, endpoints 0, 4 and 2, 0 are candidates for absolute extrema. Don't forget to always check if the critical points are in the region under discussion. The final step to this process is to collect up all the function values for x, y that we have computed in this problem. They are listed on the table. Value of x, y and value of fxy. First critical point is 1, 1. Other 0, 0. And then 2, 0. And 0, 4. And 5 divided 4, 3 divided 2. Values of f function 2, 3, calculate easily. 1, minus 1 and 2.125. So this point is max. This point is mean. We conclude that the absolute mean value of on the triangular region is minus 1, attained at the boundary point 0,4. That the absolute maximum value on the triangular region is 3, attained at the boundary point 0, 0.